Good morning, everyone. Am I audible?
Good morning, ma'am. Yes, ma'am.
Morning, ma'am.
And what about the slide? Is it visible?
Yes, ma'am.
Yes, ma'am.
Okay, so today we are going to discuss experiment number 8 of your practical course. I hope you all have seen that I have already uploaded the video of this experiment. In fact, I was supposed to take up this experiment on yes. Am I audible again? There was some interruption in the connection, internet connection. Can you hear me?
Yes, ma'am. Now it is audible.
Yes, ma'am.
And what about the presentation? Is it visible now?
Yes,
Yes,
ma'am.
ma'am.
Okay. So I was saying I was supposed to take this experiment with you on the last turn itself, but then it was announced as a holiday. So we're doing it today. It is going to be experiment number 8, and the objective for today's experiment is that we're going to study the viscosity of a given sample of any lubricating oil with the help of a Redwood viscometer at various temperatures. I hope you have studied about this property, viscosity. In fact, not only at this level, you're already familiar with the term viscosity from your basic level classes. And I hope you've studied about the Redwood's viscometer in your theory class. Have you?
Yes, ma'am. In the lubricant chapter.
Lubricant chapter, yes. So in this experiment, you will be studying the viscosity of the lubricating oil, given lubricating oil at various temperatures with the help of Redwood's viscometer. In fact, what you will be doing, you will be recording the viscosity at various temperatures. You will be varying the temperature and you will be recording the viscosity, and a graph will be plotted between the two quantities, and from the help of the graph you will have to find out whether there is a direct relationship or an indirect relationship, inverse proportional, between the two quantities, or is the temperature even affecting the viscosity or not. So this is how the experiment will be performed. Will anyone want to define viscosity first? Or a fluid, how will you define its viscosity? It is a measure of what? Nobody.
Ma'am, it is basically resistance towards flowing.
Yes, resistance, or you can say the frictional force between the layers of any fluid, or in our case, it is the lubricating oil, you can say. So the frictional force that is offered between the layers of any fluid, that you call as the viscosity. So how will the rate of flow and viscosity be related to each other? Like if the viscosity is high, then tell me how will the rate of flow will be affected
Inversely.
inversely. That
Yes,
is, if the viscosity is high, the rate of flow will be slower.
Yes, ma'am.
So in fact, this is what you will be measuring in this experiment, or you will be recording the rate of flow of the fluid. And how will that be done? Let us come to the apparatus and I will explain it to you. Yes, is slide number 3 visible to everyone?
Yes, ma'am.
So I'm just enlarging the figure. This is the setup of the Redwood's viscometer. In fact, if I tell you about the total uh, setup, it is nothing but two concentric cylinders. So has a picture been framed in your mind? Two concentric cylinders. So one is the inner cylinder, which you can call as the oil cup. In this, the um, lubricating oil, which has to be tested, will be filled, and the outer cylinder is going to be the water bath, which will be used for heating the oil that will be placed in the cup. There are two thermometers which will be recording the temperature of the oil and water bath separately. In the figure, the heating has been shown with the help of a burner, but the apparatus that you use in the laboratory, there the heating is conducted with the help of electricity. Electrical heating is done and a rheostat is involved. So heating will be done that way. And this you can see, there is an orifice here, and that orifice has been covered with a metallic gate, or you can say there is a metallic ball over here. So the cup in which the oil is filled, it is concave in shape at the bottom, and exactly in the center there is an orifice or a small opening through which the oil can flow when you will lift this metallic ball. This will act as the valve which will decide um, when the oil is flowing from this oil cup into a flask that will be placed below this orifice. So if you will remove this metallic ball, is connected to a rod. So whenever you will lift it, what will happen? The oil will start flowing, and when you will place it back, the flow will stop. So in a nutshell, if I have to tell you how the experiment has to be performed, it is nothing but what? You have to fill the oil in the oil cup. Heating has to be done. You will record the temperature, and suppose a definite volume you will allow to flow from this oil cup. So what you will do? You will lift this metallic ball. The oil will start flowing from the oil cup into the flask that is placed below. The Roush flask has been shown. It is nothing but a conical flask. And as soon as you will open the valve by lifting this metallic ball, you will start the stop clock. You have to record the time, in how much time 50 ml volume of the oil has flown from the cup into the flask placed below. As soon as the oil will reach the 50 ml flask, 50 ml level in the flask, you will stop the clock and you will record the time. So what has to be done? Then you will lower the temperature a little bit. Again, this experiment will be repeated. You will fill the cup, oil cup again with the same lubricating oil, and at a different temperature. Again, you will lift this metallic ball you will allow 50 ml of oil to fall into this full rouge flask and note the time it has taken to flow from the oil cup into the full rouge flask. So this has to repeat it a number of times, and then when you have obtained the value, you will plot the graph. So is the experimental setup clear to everyone? There are stirring blades so that uniform heating is done. Nothing else. Leveling screw so that it is horizontal according to the surface on which it is kept. So is the experimental procedure clear to everyone? How will the experiment be performed with the help of this Redwood's viscometer? Any
Yes,
doubts?
ma'am.
Yes, ma'am. Yes,
It
ma'am.
is very direct and simple. Just
Yes, ma'am.
we think of two concentric cylinders. In the middle one, you are filling oil, then you are allowing it to fall, and the same volume will be made allowed to fall every time. Only the temperature will be changed, and you will record the time, how much time the oil takes that specific volume to fall from the oil cup into the flask. This is what you have to do in the experiment, nothing else.
Hello, ma'am.
Intentionally, yes.
Ma'am, here how can we open that orifice area to
How will you
record
open?
that orifice area to record
How
50
will we
ml of that?
open it? See, there is a
Yes, ma'am.
metallic ball over here, heavy metal. Then
Okay,
there
okay,
is
okay.
a rod attached to it. So it is one device, in fact. And you will simply lift the rod and the hole will be opened.
Okay, ma'am. Okay, ma'am. Got it.
Got it? And when you will leave it, then again it will cover the hole. And because it is concave in shape, every time you will leave it, it will cover the hole. That is why intentionally this has been made concave in nature, so that you leave it in any position, but it will land into the hole. Yeah.
Yes, ma'am.
And see this part through which the oil is flowing. Again, this has been made here. The opening, can you see? This has been made convex in nature. This has been made convex in nature so that the oil, when it will fall, when it will make a droplet over here, so that it doesn't spill on the lower surface. Even it will start say spilling over the lower surface because of this specific shape, it will again come back to the center because of gravity. Is that clear? The nature at the bottom of this oil cup. So from inside it is concave and from the outside it is convex in nature. Is that clear?
Yes, ma'am.
Yes, ma'am.
And here a very specific Kulrausch law. Kulrausch law in fact is nothing but the other name of conical flask itself, but a specific one has been shown, though you don't use it in the laboratory. This has been shown specifically so that how do you place it below the orifice? You place it in such a manner that the oil droplets fall on the extended mouth of this flask, this funnel shape you can see. And what is the purpose behind that? The purpose is that frothing can be avoided, because when it will fall on this extended part and then it reaches the bottom of the conical flask or the Kulrausch flask, then frothing will not take place. But suppose if it is falling exactly at the center, drop by drop, then what will happen? Frothing will take place, and you will not be able to record the level of volume clearly. Are you getting my point? If bubbles will be formed at the surface, then you won't be able to see the level clearly. So just to avoid that, what has been done, the specific shape Kulrausch flask has been shown in the diagram. I've already explained the working, but just I will read out the content of the theory for you. So Redwood's viscometer consists of a cylindrical oil cup furnished with a gauge point or a metallic orifice jet at the bottom, having a concave depression from the inside. I told you about this concave depression from the inside to facilitate a ball with stiff wire to act as a ball to start or stop oil flow. So why has this been made concave? To facilitate this ball so that every time in whatever position you leave it, it will come back to the center only. The outer side of the orifice jet is convex so that the oil under test does not leak over the lower face of the oil cup. Of this also I have told you already. The oil cup is surrounded by a water bath with a circular electrical immersion heater. That has not been shown here in the diagram. In fact, a Bunsen burner has been shown. Otherwise, there is a circular metallic ring which can be electrically heated that heats the water in the water bath. That you will be able to see in the video that I have uploaded already. And there is stirring device as well. The paddles of the stirring device can be seen here, the stirring blades, the diagram. Two thermometers are provided to measure water bath and oil temperature under test. A round flat bottom flask of 50 ml marking is used to measure 50 ml of oil flow against time. A water bath with oil cup is supported on a tripod stand with leveling screws. There is no tripod stand. The machine that is more sophisticated, the one that you use in the laboratory, there is an electrical device for heating, and the stand is also embedded in the machine itself. So you don't have to use a tripod stand for that. You can see the picture of it in the video that has been shared with you. So this was about the apparatus. Now let us come to the procedure.
Excuse me, ma'am.
Yes.
Ma'am, what is the function of stirrer sheet that is on the that circular
Stirrer.
sheet on the? Yes, ma'am.
Why is it circular you want to know, or what is the purpose of stirrer you want to know?
Ma'am, that stirrer sheet. Ma'am, you told that stirrer blade is for uniform heating. But what is the purpose of stirrer sheet?
Stirrer sheet?
Yes, ma'am. It was a circular sheet above that, ma'am.
Stirrer blade you're talking about?
No, ma'am. Stirrer sheet. It was. It was in the top right.
Stirrer
Um,
shield is there. Okay, in the
yes, ma'am.
figure
Sorry.
it has been marked,
Stirrer
you're
sheet.
asking.
Yes.
Stirrer shield. And there is also a cover, actually. Stirrer shield has been mentioned. Actually, this whole device can be dismantled. You can see that in the video. In the simplistic way, there are only two concentric circles and you place it one by one. Means you place the stirrer shield, the whole device that will introduce the stirring mechanism into the apparatus, or you can say between the two cups. It is somewhat separated, and in fact you can say it is in fact the third concentric circle that will enter between the two cups. So it is going to be something that will be enclosing the oil cup completely here with pedals, and then there will be a lid that will be placed on the cup. Then there will be another mechanism, in fact stand for placing the two thermometers. This has been shown very clearly in the video that has been uploaded. So this can be separated in fact, and because it is enclosing the oil cup, I think that is why it is being called the stirrer shield. Is it clear?
Okay, ma'am.
See the video, that will help you to understand better. So now, is slide number 4 visible to everyone?
Yes, ma'am.
Coming to
Yes,
the
ma'am.
procedure, these are basic things which you will generally not do with the machine on which you have to work on. The apparatus definitely is clean first, but the leveling of the screws has not to be performed. But if you're using the older version, in that the leveling of the screws is also to be done initially. Then, when marking the viscosity determinations, the bath is heated to a few degrees above the desired test temperature. So if you want the temperature of the oil to be say 42, definitely the bath say will be heated to 44 to 45 degrees. So the bath will be heated, water bath. The test sample is adjusted until the sample in the cup is at the test temperature, stirring the contents of the bath and the cup during this process. So the oil will be filled in the oil cup and you will adjust the temperature such that the sample under testing attains the temperature which you want it to attain, and in the process stirring will be maintained. When the temperature will become steady at the desired value, then what you will do, you will adjust the level of the oil in the oil cup. Generally what is done, if you want to collect 50 ml, 50 ml is the mark in the oil cup itself also. It is the same. So there is a mark in the oil cup itself, say up to the 50 ml mark. And if you wish to fill the oil up to that specific level, either you can be very specific for it, but if you have exceeded the limit, there is no problem. You can lift the ball and the extra oil can be collected in a different, say, a conical flask to adjust the level. The way you do it in the burette reading, don't you fill the burettes in the same manner? Means you fill excess of it and then you allow it to flow from the opening so that it is adjusted to the zero level mark. So have you followed this point? How will you adjust the mark in the oil cup? A little excess will be filled in the oil cup and you will allow the excess oil to flow into, say, another extra vessel, such that the sample touches the filling mark in the oil cup. These are the initial arrangements that you have to do. So is it clear up till point 3?
Yes, ma'am.
Oh. Slide number 5, is it visible?
Yes, ma'am.
The oil cup is covered. Thermometers are inserted. This is not very appropriately written here in the lab manual. I'm following what has been shared in the lab manual because the second point itself, they have said that you need to adjust the test temperature. So without a thermometers, how will you be able to see? Thermometers have been inserted initially itself. Then a clean and dry standard 50 ml flask is placed centrally below the jet properly. So this is the Rouch flask they are talking about, which will be placed below the opening or the jet. So a clean and dry standard flask will be placed. The valve is lifted and the stopwatch is started simultaneously. So as soon as you will lift the valve, you will start the stopwatch. And the valve is not removed completely, means it is not like a spoon that you will remove it from the oil cup and you will place it on the surface on which you are performing the experiment. There is a hook there on which you can actually suspend it in the machine itself. So it is not removed completely, it is allowed to remain immersed in the oil cup itself. The valve is not removed completely but kept immersed in the oil by supporting it by the hook provided for the purpose. So you will not remove it completely and place it on the table on which you are working. The receiving flask is positioned so that the oil strikes the flared mouth, I was saying the extended mouth, and does not drop directly into the opening, which would cause foaming. So if foaming will be caused, again I told you, that will restrict you from recording the level of the volume correctly. The stopwatch is stopped when the level of the oil reaches 50 ml mark in the neck of the flask. So as soon as it reaches 50 ml mark, you will stop the stopwatch and you will note down the time. The time elapsed in seconds is recorded as Redwood viscosity at the test temperature observed before the flow was started. So when you started the flow, at that point of time, the temperature is recorded. And after that, you check the time elapsed for the 50 ml to get collected in the flask placed below the orifice. And following the same procedure, the viscosities are determined at one or more temperatures. So this is the procedure that you have to follow. I have explained it in detail, in fact, before these points itself. So is it clear how you have to perform the experiment?
Yes, ma'am.
Yes, ma'am.
Okay. Now coming to the observations. Slide number 6, is it visible?
Yes, ma'am.
These count of thermometers you need to mention. There are two thermometers. You can mention T1, T2. It is the same for both of them. These count of thermometers. It is the same. Then the observation table that you will make. Typically, there are two, in fact, columns. Since you have to plot the graph, tell me which is going to be the why are we placing the temperature on the x-axis? In fact, that is going to be a better question. Why are we placing the temperature on the x-axis and the time taken on the y-axis? Like, what is the convention? How is this decided? What should be placed on the x-axis and what should be placed on the y-axis while plotting a graph?
Ma'am, the quantity which is independent that is to be placed on the x-axis and temperature is
Yes, that
independent.
is absolutely right. The independent quantity should be placed on the x-axis, and the one that you are recording, or the dependent one, that should be placed on the y-axis. So temperature is the independent quantity. You are bearing this, and with respect to the change in the temperature, you are recording the time taken. So say at 5 temperatures, you record the time taken. Please take a screenshot of this slide so that you can record the observations. You can record the observations in your practical files, or you can even note it down. So at a temperature of 54, say 100 is the time taken. The trend you can see from the observations itself, and that is obvious as well. As the temperature is decreasing, what is happening to the time taken?
It's increasing.
It's increasing. So the relationship between the two. See, here the relationship is between temperature and time. And you are studying the viscosity. I want you to answer what is the relationship between temperature and viscosity. How is time related to viscosity? If the oil is more viscous, will it take more time or
More
less time?
time.
More time.
More time.
More time. What is the relationship between time taken and viscosity? Is it direct or inverse?
Direct.
Direct. So whatever relationship you get between temperature and time taken, that means that is going to be the relationship between temperature and viscosity as well. Yes?
Yes, ma'am.
Yes. So please note down the observations from this table, and you have to plot a graph between the two quantities, temperature and time taken. And this is an instruction that take the scale for the two axes to be the same. Axes, in fact, the plural of axes is axes, A-X-E-S. Take the scale for the two axes as same and mention the scale on the graph itself. Should I move to the next slide?
Yes, ma'am.
Yes.
And finally, the result. The viscosity of the given sample of lubricating oil determined with a Redwood viscometer varies dash with temperature. So you will simply furnish whether it varies directly or inversely with temperature. One more small point about the plotting of points on the graph. Can you see these 2 points on the slide? One is this dark, complete black circle and a small point here. This. Is it visible?
Yes,
2
ma'am.
points.
Yes, ma'am.
I just wanted to talk about how you plot a point on a graph. See, I think everybody knows that point is a dimensionless quantity. It has no length, breadth, or height. Yes?
Yes, ma'am.
So when you make a point, it should be made with a very light hand, a pencil you will be using on the graph. Now, if that point has been located on the graph, there is a possibility that it won't be that much visible. Yes? There may be a possibility that you're not able to see it very clearly. So in that case, what students actually do, they circle it again and again and make it a very dark spot. This is what they do. In fact, ideally, a plot should be pointed with a very sharp pencil and with a light hand. Even if if you do not use a sharp pencil, then again, a dark dot can be seen in this manner. So this is not how you plot a point on a graph. And as far as the visibility problem is concerned, what should be done if you think, in fact, this is what is done. You make a point, you locate it on the graph, and then you circle it with the help of the pencil again. So that circle actually highlights the point on the graph. Though the circle will not be of this kind, I could not make it with the help of PowerPoint on this slide. Simply, you will locate the point on the graph and circle it with a pencil and not do it this way. This is going to be the correct procedure. Simply circling it, not a dark circle. Again, a circle drawn with a very light hand. Is it clear? How will you locate the points on the graph?
Yes, ma'am.
So 2
Yes, ma'am.
instructions I have given. How you will locate the point on the graph. That should not be a very dark circle. A point made with a sharp pencil with a very light hand, and then you will be encircling it. And the scale should always be stated on the graph paper that you are using. And ideally, the scale should be chosen in such a manner that at least more than half of the graph paper is used, the one that you are using. It's not that the graph paper is of the size of your practical file and the graph is just in one corner of the graph paper. It should be at least more than half of the graph paper in size. It should cover 3/4, in fact, at least 3/4 of the graph paper. Is it clear? So these were some instructions regarding the plotting of the graph. Are there any other questions from today's experiment?
Ma'am, hello.
Yes, yes.
Ma'am, in case of well, can we do this by any liquid like water or anything?
Whether you can do it with water or not. See,
Yes,
you are
ma'am.
interested in finding out the viscosity. Means you want to know whether the viscosity of water can be found out with the help of this apparatus or not.
No,
This is what you're asking.
for for any liquid.
Whether the viscosity can be found out or not. This is what you're asking.
Yes, ma'am. How it is varying?
Varying definitely can be studied. The variation can be studied. There is no doubt in that. Because you are with this, what you are doing in principle, what you are doing, you are actually monitoring the rate of flow of that liquid or fluid which will be filled in the cup. Yes. So if you
Yes,
are
ma'am.
indirectly measuring the rate of flow, definitely you can predict the variation of viscosity with temperature. That you can do.
So, ma'am, we can
But
simply
the
say
thing
that
is, what is coming to my mind, suppose water, it has a better tendency to flow, means the viscosity is low as compared to oils. So what can happen actually, suppose you vary the temperature, what have we done in our experiment?
ma'am, the
Just wait.
viscosity
How much
increases.
have we varied the temperature? Suppose you're varying it by 6 degree. Here you are observing the change. If you have varied it by say 5.5 or 6 degree, there is a change in time taken. Whereas in the case of water, what can happen? This change can be really very slow, very small, so small that even the observation cannot be seen. So you need to see how much temperature difference has to be taken for a specific liquid for the time to be observed distinctly. Are you following my point?
Yes, ma'am.
So that can be the case. And the oils that are used for this specific experiment, they give uh, quite visible, observable changes in the time taken in small intervals of 5 degree temperature change. This will not happen with water. There, the temperature change, in fact, otherwise, in that case, we have to take a stopwatch that is more precise, means that has a lower least count. Because here, the stopwatch that has been taken, it has a least count of 1 second only. So if that you do, even that can be helpful. That can be recorded. Is it clear?
Yes, ma'am. So, got it.
Yes. Any other question? So if you do not have any other questions, first of all, I'm stopping the recording.